Good morning, we are group 2 and we are going to introduce APT, which is atom probe tomography. Let's begin. The contents are composed of 6 chapters. First, principles. In this chapter, we are going to discuss APT's principles and techniques. Maybe this graph would be familiar with you guys. As you can see, APT is at the upper left side of the graph, which means high resolution and detection limits. Then, where does this high resolution come from? The first reason is the short travel time of evaporated ion. In APT, the evaporated ion travels the tens of picoseconds to reach the local electrode, which can minimize time-varying field. Since the energy deficit of the field is main reason which hinders the resolution, this factor is important. Next one is wavelength of the laser. According to Bunton's research, shorter wavelength laser can improve the mass resolving power. And APT uses UV laser, therefore it has high resolution. Lastly, the cryogenic temperature of the sample limits thermal motion and makes preferential evaporation possible. APT is a combination of ion projection and time-of-flight mass spectrometry (TOF). A surface atom from apex of sharp needle-shaped specimen, usually less than 100 nanometer radius, is removed by field evaporation. Field evaporation is the field-induced removal of an atom from its own lattice. Field evaporation involves the ionization of these surface atoms, whereupon they are subject to an electric field force that causes them to accelerate towards the detector. The evaporation event follows immediately after the ionization of surface atoms, and this ionization is induced by the combined effect of standing electrostatic field and either a high voltage or laser pulse transmitted to the surface atoms of the specimen. The TOF of ion is defined as the time between the application of the pulse that triggers the field evaporation and the moment when the resulting impact is measured by detection system. The TOF of ion is directly related to its kinetic energy. As the ion is accelerated by the electric field, it acquires the potential energy. By equating these two energies, a mass-to-charge ratio of the ion can be obtained. From mass-to-charge ratio, the identification of its elementary nature is become possible. In the operation of delay line detectors, the electron cascade produced by the impact of an ion on a microchannel plate (MCP) stack. Specifically, the MCP assembly is an array of microchannels. Each of them is an electron multiplier tube. When ions enter the microchannels, they hit the wall, resulting in a cascade of electrons. The cloud of electrons propagate the microchannels and hit the grid of wires, which is the cross delay line anode (DLA). When the electron cloud hits the grid, the two electrical signals are created and travel through the end of the delay line like this. Detecting these signals, which arrive at different timing, enable the impact coordinate like this. Next is the techniques for APT. Field evaporation is an important part of APT. The major two techniques for field evaporation are high voltage HV pulsing techniques and the laser pulsing techniques. The first one that we will discuss is HV pulsing techniques. When using HV pulsing to achieve field evaporation, fast HV pulse of a few nanoseconds are used. As the field evaporation is a probabilistic phenomena, not all of the atoms will be field evaporated at the very same instance across the duration of the pulse. Depending on the instance at which the ion is created, it will be accelerated by a different stage of a varying field and so will not necessarily acquire the full energy of the pulse. Generally, this effect is referred to as energy deficit. The left figure here shows spread in the energy of the ions, which is reflected in the shape of the mass peaks. The peak generally display a sharp rising edge and a long tail corresponding to the ions that had an energy deficit. This can greatly reduce the mass resolving power and sensitivity of the instrument. To correct this, time focusing techniques have been developed. Ions entering in an electrostatic field with a lower energy will be deflected first and will therefore have shorter flight paths than the ion with high energy. A longer flight path increases the time of flight of the ions. Thus, it is possible to have ions of the same mass to charge but with different energies arrive at the detector with a similar TOF. However, HB pulsing technique can only be applied to metallic materials. If specimens have a high resistivity, the shape of the fast-varying HB pulse is attenuated, which leads to a wide variation of an electric field with time. This distortion markedly degrades the timing resolution, which in turn degrades in mass resolution. To overcome restricted application of APT, a few pioneers suggested the use of light source for field evaporation. There are three different paths that could lead to the photon-assisted field evaporation of surface atom. First, an electron from the surface adapton can directly tunnel into vacant bulk electron state. Second, the electron from the adapton can be excited by the resonant absorption of one or more photons. It can consequently tunnel into vacant level inside the conduction band. Third, the absorption of photon by electron in the material, creating hole inside the valence band and providing the opportunity for electron from the adapton can tunnel directly into valence band. Among these three different passes, the third process is most dominant process at low temperature. Now, let's take a look at 3D reconstruction. In every pulse, 2D data, X and Y coordinates are detected. What we need to do is convert this data into 3D image, X, Y, and Z coordinate. 3D reconstruction is composed of two parts. One is magnification and the other is depth coordination. Before 3D reconstruction, two major assumptions are required. First, end of the tip is considered as hemisphere on a cone. Second, average atomic volume is constant. First, magnification. Point projection model is the basic principle of magnification. Figure here is a schematic view of magnification. Magnification constant m is defined as data distance from axis divided by real atom distance from axis. Because tip size is much smaller than the distance between tip and detector, magnification constant is usually in the scale of 10 to the power of 6. By dividing detected data with magnification constant, real x and y coordinate of sample can be obtained. To obtain z coordinate, we stack each layer of atoms. For each pulse, thin layer of atoms vaporizes. Therefore, by calculating dz, which is remote depth per each pulse, and adding them all with this correction factor, it will give z coordinate. dg is obtained with atomic volume divided by detector efficiency and volume per layer. Obtaining reconstructed coordinates are summarized in this figure. Because this method is the most fundamental method, it has some limitations. To deal with this, several researchers developed some method to correct these limitations. In actual APT, pre-programmed software reconstruct data into 3D. Next is sample preparation. Sample preparation is one of the most important parts in APT. Well-prepared samples give better resolution and better 3D reconstruction. APT sample should be in sharp needle shape with radius of 10 to 100 nanometer, smooth or polished surface, and circular cross-section. FIV lift-out method is one of the most powerful methods to prepare sample. It is composed with four parts. First, sample is prepared in thin film, and with TEM, area to analyze is determined. After determination of area to analyze, protective layer is deposited on the sample and cut into wedged shape. Next, wedge sample placed on holder to weld and cut the useless part. Finally, annular milling is used to sharpen and polish the sample into needle shape. These are the actual TEM image of sample preparation.
Okay, now let's move on to the APT instrument. We talked about very fundamental parts of APT so far. However, from now, we will take a look at more practical area. Historically, there have been many different types of apparatus for APT. However, today, the most common design for APT is the local electrode atom probe, shortly called the LEAP. The modern LEAP system mainly consists of the five essential parts: a vacuum system, local electrode, detector, pulsing system, and cryogenic system. However, we already introduced detector and pulsing system in the previous sections. So this time, let's look into the other three parts in detail. First, the vacuum system. You should remind that APT is the technique detecting the flying ions generated by field evaporation. So you can find that if there is something to disturb the ion flight path, it can seriously affect the analysis result. Therefore, it is extremely important to keep ultra-high vacuum condition for APT. In the lab system, there are three different vacuum chambers to accomplish high vacuum quality of the equipment. The load lock chamber and buffer chamber allows fast specimen loading from atmospheric pressure to high vacuum conditions. The main analysis chamber is the very place where field evaporation and ion detection occur. So this chamber should always be kept under UHV conditions. The next part is the local electrode. The local electrode is funnel-shaped aperture with diameter of 40 micrometers closely located at the apex of the specimen. The shape and configuration of the local electrode is pretty important because it creates and confines the electric field to the very small specimen tip. This helps field evaporation take place more easily by reducing the voltage that has to be applied to the specimen. The last part in APT instrumentation is the cryogenic system. For APT, the sample needs to be held at a cryogenic temperature to limit the thermal motion of atoms and preferential evaporation. Because the thermal vibration of atoms influences the accuracy of analysis results, it is required that the cryogenic system keeps the temperature of the sample very low. Specifically, most modern LIB system uses a closed-cycle helium cryogenerator to provide very low temperature condition. This type of cryostat lowers the temperature by removing the heat generated during compression and expansion of helium gas. Okay, let's go to the application part. Now we'll talk about how APT is being used in real research. As you can see in this slide, there are many research fields APT can be applied. APT is a powerful technique to find atomic structure and chemical composition in many kinds of materials. Therefore, it is appropriate for researchers to explore inside the material at atomic scale. This time, we'll introduce one of the examples in the field of the electronic device where APT is the most commonly used. This paper, which was published in 2016, the authors analyzed silicon nanowires to figure out the diffusion and segregation behavior of several dopants. Let's look into some data obtained from APT. This is the figure set from the paper. The left image is the cross-sectional SEM view of the sample. As we described in the previous fundamental part, protective platinum layer and zinc oxide encapsulation layer are observed. After ion beam milling process, 3D reconstructed image was obtained. We can see directly the composition and location of individual atoms in the sample. This is exactly what we can obtain from APT. We can also get the mass spectrum corresponding to the 3D image as presented in this page. Someone can say the figure A is similar with XPS survey, and that's true. For more precise analysis, the authors pick up small areas of the spectrum near dopant peaks. However, we must consider the tailing effect when we deal with the background level. In this case, phosphorus peak is overlapped with silicon peak, which leads to higher background for phosphorus. Then the authors controlled the diameter of nanowires and observed the diffusion and segregation of each dopant from APT data. So far, we have learned the application of APT. Before the end of the presentation, we would like to summarize the strengths and limitations of APT. Since we already discussed a lot about the strengths, this time, let's take a look at the limitations of APT briefly. First, it is site-specific. We should select small specific area of the sample for APT, so it requires complicated sample preparation process which is time-consuming. Also, due to high resolution and detection limit, the statistical accuracy is limited. In other words, while collecting large data set, the smaller change due to sample stability can affect the accuracy more seriously in APT rather than other techniques. Lastly, it is destructive. Because the sample is evaporated during APT, it cannot be used again anymore. Now, you know that APT is a powerful analytical tool, but there are a number of limitations as well. So, if you use APT, first you should find whether APT is appropriate to analyze your sample. Okay, this is the end of the presentation. Thank you for listening, and now we'll have a Q&A session.